Okay, so x squared plus y squared plus z squared equals 100 is a quadratic surface. You know, say x squared plus bx plus cy squared plus dy plus z squared plus fz plus f plus g equals 0, right? I think that's what I wrote down last time. I'm not sure what letters your text uses for, but there it is. Okay. And for this one, A, C, and E are all 1. The coefficients of x squared, y squared, and z squared. All the other coefficients are 0. And that G out at the end is negative 100. So that when you put it on the other side, it's 100. Okay. So this is a quadratic surface, but we immediately should recognize this. From 0 to point x, y, z, your distance is square root of x squared plus y squared plus z squared. That's just an extension of the Pythagorean theorem. Okay. I mean, it is Pythagorean theorem applied twice. And then if we square that distance, we get x squared plus y squared plus z squared, meaning that the distance from the origin to x, y, z squared is 100. Okay. Square of the distance from the origin to x, y, z is 100, meaning the distance is 10. And all the points at distance 10 form a sphere of radius 10, center at the origin. And somebody said immediately, it's a sphere of radius, center at the origin of radius 10. Okay, said about that, I think it was good. So, okay, well, what if it was now x squared plus y squared minus z squared equals 100. Now, one way of looking at this is in planes parallel to the xy plane. And we can kind of do that with forms. I would say it's okay, this is the same as x squared plus y squared is 100 plus z squared. In x and y, this is a circle. The radius 100 plus z squared. Radius of square root of 100 plus z squared. Okay. So in a plane, z equals whatever. Okay, C stands for, C is a number that we plug in for Z. We get this. Does that exist for every possible value of C? Well, yeah, it does. Okay. That circle exists for every possible value of C because 100 is positive and C squared is positive, so we can always get the square root. And the further C is, like in the Z direction from the origin, the bigger the circle is going to be. Okay. So we get bigger and bigger circles. Now, do they get bigger linearly? Well, no, that's not a linear function. So how do they get bigger? Let's say we'll do it in y and z. We have y squared plus z squared equals 100 minus x squared. Okay. This is a circle. of radius 100 minus x squared. It only exists if the magnitude of x is less than or equal to 10, because the square of your radius can't be negative. Or looking at it differently, if the absolute value of x is more than 10, then this is negative, and two squares can't add up to a negative. Now you can kind of put that together into a picture of this surface. There's more you can do though. Okay. Oh, wait a minute. Yeah, that's completely wrong. Y squared minus c squared, isn't it? So this isn't a circle. It's having trouble seeing where that was going to go. All right. I think as I was visualizing it, I would see in a circle. So if there'd been y squared plus c squared, everything I said would have been correct. Anyhow, what's this? This is a hyperbola, right? I mean, yeah, you get like y squared over a minus z squared over b equals 1, which is what you have if you divide both sides by this. And that's got to be something that's kind of a habit. You've got to know what conic section you're getting. Okay. In y and z, you now get the rectangle that I advise you to use to visualize where hyperbola or ellipse or parabola, well, hyperbola or ellipse is, okay? And you have line segments through it. And your vertex. Well, is your vertex on the y-axis or on the z-axis? Okay. If it was on the y-axis, then you'd have to be able to say z is 0, and that works. So this is going to be in y and z coordinates. This point is going to be and this will be minus that. And there's your hyperbola. So on the YZ plane, you've got a hyperbola that intersects here. In the XZ plane, that would be a plane here. You've got a circle. Something wrong. Sorry, it's not XZ, it's XY. In the XY plane, you've got a circle. So down here in the XY plane, you've got a circle. Then as you go higher and higher in the XY plane, if you get out to Z, we'll see here. Here's another plane, and you get a bigger circle. And this bigger circle also, the circle intersects these two hyperbolas. The circle will intersect this hyperbola here and over here somewhere. And it'll go back maybe to here. It'll be a bigger circle than the one we just drew. It's gonna look a lot like the picture we had last time if you start shading. And you're gonna end up seeing, as you go higher and higher, these circles get bigger and bigger. They gotta get bigger and bigger because they gotta meet these hyperbolas. Okay. Now you have a symmetry between the X and the Y. So you just do, this thing becomes just a solid of revolution of these two hyperbolas, not that circle. Okay. And it looks like this, it's hollow in the middle. It's got a name. And there it is again. And just by using X, Y, and Z with coefficient 1, you gain a lot of insight. Now, if you got a bigger number, you've got different numbers on X and Y, well, that just makes this circle into ellipses. Okay, every circle is an ellipse. They keep getting bigger because you're still going to get this on the other side. So you want to try to work out the intricacies of that. Okay. So you want to keep thinking about these things because the better intuition you have on these, the better you're going to be able to visualize the rest of the stuff that happens in 3 dimensions. And 3 dimensions is imminent, like starting right now. Okay. Then you ask questions, you know, like, if you had one of these turned upside down, and you just take this section of it, it gives you a function, okay, above the XY plane. And you can ask questions about what's the vector normal of this function at a given point, okay? Oh, you can do that regardless. And we got to learn how to do that. So we're going to need to use sometimes cylindrical and spherical coordinates, as well as rectangular coordinates. So we're going to develop that right now. I think we had a question, so let me. Okay, I got a series of good questions. We finally got down to it boiled down to, why is it rotated about the Z-axis? Okay. Well, you see a symmetry between X and Y here. There's no symmetry with Z because you got the minus. So if you're looking at planes parallel to X, go XZ plane or the XY plane, you get exactly the same thing. If this was X and this was Z, we'd have exactly the same equation, except it would be an X and Z. So what that comes down to is what we did in the YZ plane. You got a hyperbola that looks like this. In the XZ plane, so here's X, and here's Z. Your rectangle, in this case a square, is here. And your hyperbola comes out toward us this way and back away from us that way, which is exactly what this thing is doing. Okay. So it's exactly the same in the XZ plane as in the YZ plane. And it follows, say a little more, that it wouldn't make any difference if you chose to put as long as the Z axis is vertical, it doesn't matter where your X and Y axes are down here in the plane. So you can rotate the XY coordinates about the Z axis. And now your Y coordinate would be maybe out in this direction, but you'd still have exactly the same shape. That makes sense? I mean, I could really break it down, but we really don't have time to do that in class. But think about it a little more. If you want me to, I'll just write it out for you. I don't think they're really going to, anybody's really going to look at it. I don't want to take the time to do that. I'm not going to look at it. So you can ask. It's just, you ask me to write that out, you're committed to look at it and come back and tell me what you learned. Okay. Okay, well, again. Any plane, any vertical plane. Any plane through the z-axis is going to cut this thing identically. Okay. And it's pretty easy to write that out. But we need to move on to make sure we understand cylindrical spherical coordinates. So we be sure to do that. So if you want to come back to this, sometime when we have time, I'll be glad to put all kinds of notation in the board. That also gets into the whole idea of rotation of coordinates, which we don't do too much of in this course, but it's important. It's kind of hard because first place, it's kind of hard to derive. Is that fact that the cotangent of theta, 2 theta is equal to this thing or that thing. It's not worth the time. If you ever have to get into it, just brush up your trigonometry and you'll be able to do it. It's supposed to have been done in pre-calculus 2, but I don't think many people have done it pre-calculus 2 in the last 20 years. Okay, I love it, but it applies here. That's where you have, in addition to x squared and x and y squared and y and z squared and z terms in your quadratic form, you have xy, xz, and yz terms. Okay, and those terms just accommodate rotation coordinates. Okay. And rotation groups are a whole lot of functions. So if you want to get into it, we can, but we're not going to have time. Good, but we should have time. It's beyond the scope of this course. Probably throw me in Guantanamo for teaching if I, in this course, you know. So, all right. First of all, let's review polar coordinates. I'm not going to review polar coordinates. I'm going to say a few things about polar coordinates. First of all, I should have drawn a circle first, but that's worse. Okay, here's a circle. I'll go into this quadrant because that's a better part of the circle. So we got radius r, and then another circle. I'm not going to draw the whole, well, so the radius of this circle is different than the radius of this circle. I was going to say what it is, but I'm just going to do this. This distance is delta r. So this is r, and this is r plus delta r if you wish. We're not going to really use r plus delta r. Okay. Here's angle theta. And in here is angle delta theta. Probably can't read it, but just two angles that are separated by delta theta. Okay. Now, what's the shape of this region right here? What are the dimensions of this region? Let's draw a bigger picture of it. Draw it big enough that we can label it. And what's its area? Okay, some people have a premonition of what's coming about here, but, right now. We want to talk about the dimensions of this thing, and somebody did tell me that the exact area of this thing. Is what? It's. Pi times the square of r plus delta r, which is the area of the outer ring. Minus pi r squared, which is the area of the inner ring, right? Multiplied by delta theta over two pi, which is a portion of this thing that's in that ring. So that's good, but that's not going to be very helpful. Okay. But it's exact, and we're only going to get an approximation. But the approximation is going to be useful. Other people have premonition, there's some integrals coming. Yeah, that's an area increment. Yeah, area increment's a real important thread of it, right? Okay, so we asked a question, okay, we want the dimensions of this thing, because what I said was the dimensions and then the area. Okay. And since the exact area is mentioned, we'll see how the dimensions approximate the exact area. Okay, so we've got two arcs and two straight lines. Can you tell me how long one of the arcs is or how long one of the straight lines is? Well, somebody wanted to pick a straight line first, that would be pretty natural. And the length of the straight line is just a distance from here to here, which is delta r. Distance between the circles. And this is also delta r. Now, what's the length of this arc? Okay, so just to summarize what we said, somebody said, okay, it's going to be 2 pi r times delta theta over, and I finished it for 2 pi because that was coming. Yeah, 2 pi r is your circumference, and delta theta over 2 pi is the proportion of the total 2 pi radian angle, right? And 2 pi r divided by r, the 2 pi r divided by 2 pi is just 2 pi r delta theta divided by 2 pi, just r delta theta. So you get to it that way, but you get to it directly from the definition of a radian. The default unit of the angle, of course, is a radian. Okay, a radian is an arc, well, the angle of an arc, such that the arc distance is equal to the radius. So if you have half a radian, you'd have an arc distance of half the radius. If you have angle delta theta, then you have delta theta over 1 times the radius. So it needs to be second nature. You need to understand radians. So anyhow, this is r delta theta. What is it here? Okay. Now, if this is small, that arc is nearly a straight line. The arc distances are nearly the same. So what we have is pretty much a parallelogram. Even better, it's a rectangle, because these angles are all right angles. radial line is perpendicular to the arc of the circle, right? Just basic sixth grade geometry, okay? Which nobody ever learns because it doesn't get taught, but I think everybody's aware that the arc of the circle is tangent to a line from the center out to the circle. That's important. We prove it, and probably will here in the next couple of classes. Okay. What it then comes down to, and I'm gonna skip a couple of steps, because what we do with area increments is we take some point, an arbitrary point. R star theta star within the increment. And we do the arc length along here. And we do width through here. We do these two dimensions. And assume rectangle delta R by R star delta theta. In the limit, as both delta R and delta theta approach zero, you approach the state where it doesn't matter what point you use in here, because whatever R star is, it's really close to R. And that's about all you need. And this thing is really, the arc is really close to a straight line. The angles are all right angles in every case. So it's really close to a rectangle. So we can assume that this is the rectangle, and you can prove that rigorously. It should have been done in calculus somewhere in your book if it wasn't done in class. We have delta R by R star delta theta. So the delta A, the area, is this, which approaches your area increment when you do an integral of in a plane region. Your area increments RD theta. Okay. That should be somewhat familiar. Because it's how you set up intervals. And now we got to do that in space. So we can set up volume intervals. So you want to maybe review what you did with integrals, or what your text at least said about integrals in polar coordinates. How do you develop them? How do you use a partition and a limit of a sum? A Riemann sum type thing. Okay, well, that's what I really want to say about polar coordinates. Now, cylindrical coordinates are actually pretty easy once you have the polar coordinates. Okay, cylindrical coordinates in three-dimensional space. So we're going to use X, Y, and Z axes as reference points. But if we want to do this in terms of R theta and Z, which are our cylindrical coordinates, means we've got a point down here in the YZ plane. Theta is the angle from the x-axis. This point then is just R theta in polar coordinates. You're familiar R theta. Okay, it's got length of R. So this is R theta 0 because it's down on the XY plane. Now, if we raise this thing up. It's now R theta Z. And we'll get that, we'll make a little rectangle out of this. And of course, the angle between here and the x-axis and between here and the x-axis, it's right angle. Wise in this direction, it's rotated out about this much. Does that make sense? That's pretty easy to see in the picture. Hang on a minute. Okay. Well, that's pretty much it, except maybe we want to figure out what the X, Y, and Z coordinates would be. But the X and Y coordinates are just straightforward from what you know about polar coordinates. You know, I mean, polar coordinates. This is R, this is theta. Then X equals R cosine theta. And Y equals R sine theta. That's just the definition of sine and cosine. So same as true over here. We can draw it. Here's X. And here's a right triangle. Theta's here. This side is R sine theta. This side is R cosine theta. Just looking at this triangle. Okay, so this is and Z is just Z. It's the same in rectangular as it is in polar. Okay. So we have, you'll see what I said, you see that the conversion from polar, from cylindrical to rectangular is X equals cosine theta, Y equals R, X equals R cosine theta, Y equals R sine theta. Okay, and Z equals Z. Polar coordinates are natural for representing circles. And then there are a lot of other shapes, luminescence and roses and all the stuff that you see in polar coordinates. They're very difficult to, I would say very difficult, they're considerably more difficult to represent in rectangular coordinates. So if you're trying to integrate over one of those regions, you want to do it in polar coordinates. Now, in cylindrical coordinates, not surprisingly, cylinders are natural. You just let R be constant, and you get a circle in the XY plane, and then Z can be whatever, and you have a cylinder, right? All the points above and below a circle, which is just R is constant. So if you want to integrate over a cylindrical region of space, you just let R equal whatever the radius of the cylinder is. The radius of the cylinder is A, R equals A. If the cylinder extends 15 units high, you probably let Z go from 0 to 15. But we might have reason to go from -7.5 to 7.5. You got some kind of symmetry in whatever function you're trying to integrate. Okay. That makes sense? I mean, it makes sense that that's easy to describe in cylindrical coordinates, a little harder in rectangular coordinates. Because in rectangular coordinates, how do you describe a circle? Well, it's like x goes from negative a to a, and then y goes from the square root of a squared minus x squared to negative square root of a squared minus x squared, or vice versa. Okay? And if that's not something you really remember, again, you need to do a little review. They'll come back to you. Presumably, you did integrals over circular regions in the calculus course. If you didn't, there's some things that are going to be a little less natural to you when you do it here, but it's not that hard. You've got to do spherical regions and elliptical regions and, you know, all kinds of things. All right. We got to know the geometry. We'll talk about it. It's not that difficult. Just make sure you spend time on it. Make sure you really pay attention to it. Okay, the other thing about cylindrical coordinates is write it in a different color. To distinguish it. That's what it's all about, distinguished. The way I do r and theta is the arctangent of y over x, but the arctangent of y over x is between negative pi and pi. At negative pi over 2 and pi over 2. Okay. And between negative pi over 2 and pi over 2, the x coordinate is always positive. But there are angles between pi over 2 and negative pi over 2 as you go this way. Okay. And they differ from the angles you have here by pi, or 180 degrees. Kind of diametrically opposite through the origin. So you got to know that. So I qualify this. That's my rule. Whatever rule your book wants to tell you, they're telling you the same thing. Okay, they might just phrase it differently. And then z equals z. So if you have the r theta z coordinates, you easily get the x, y, z coordinates. And if you have the x, y, z coordinates, you can easily get the r theta z coordinates. Make sense? I'll talk about the volume increment, but the volume increment is really pretty simple. I'll kind of draw it now, then we'll maybe say a little bit more about it. First of all, you do an area increment. Down here. So if you got two angles theta, and you got a delta theta between those angles, it defines, and some value of r, it defines an area increment, some delta r. So that's this. This is down here. It's not going very well, but we'll have to label it. Okay. Now, if you want to raise it up here, well, you get the same increment here. Just a copy of this one, even though it probably doesn't look like it. And it's got a delta z in it. Its volume, you see better pictures in the book. Its volume is r delta theta, which is the area of the base Z is perpendicular to the plane of this thing. So your delta Z is an altitude. And your volume is R delta theta delta Z. That makes sense? Can you visualize it? You've got one of these down here in the plane. Z's coming out at you here. So you come on up to where your R theta Z is. R theta is whatever it is for this thing. That doesn't change. Comes out here. And your delta Z is this much. So you've got this thing here with this much area. Where is it? There. Okay. And it should be on a spot. But you got that much area. And then you multiply the area of the base by the altitude and you get the volume. If you don't understand volume is area of base times altitude, get used to it. That's what it is. They teach it to you in earlier courses as a formula rather than an idea often. About half the students seem to come in here knowing it's area of the base times altitude. The other just thinking it's some formula they memorize and never remember. Okay. Area base times altitude. If it comes to a point from the base, then it's 1/3 area of the base times altitude. Okay. Pyramid or cone. Altitude measured perpendicular to base. Okay. Again, I can't teach you that. I just got to refer to it, sort of out if you need to, if you haven't seen it. And if you haven't seen it, I always say this, it's more an indictment of the curriculum that's been adopted than the teachers that have to teach it that way. But it's a serious indictment. Why is it? This thing is, well, it's there. Okay. Okay. Now, spherical coordinates get a little more complicated. The picture is a little more complicated than this one, because this is just basically something close to a rectangle down in the plane, then you give it some depth. Okay. And that's not difficult to understand. Spherical coordinates. Now I'll just locate a point using rectangular coordinates, so you know what X, Y, and Z are. So I could easily get R, or you got R here. Then you got theta. And you got Z. Then you can go from rectangular, cylindrical, or cylindrical to rectangular, but now we want to go to spherical. And in spherical coordinates, spherical coordinates, we go directly from the origin to the point, and that's rho. Okay. Instead of R, we use rho just so we don't get confused when we're writing this out and write an R and then think we're in cylindrical. Okay. Or polar. So there's rho. Theta is the same as it is. I'll just kind of circle theta. It's the one that's common between cylindrical and spherical. Rectangular has nothing in common with spherical. Okay. rectangular has Z in common with cylindrical. Cylindrical has theta in common with spherical. But there's nothing in common between rectangular and spherical. Okay. So the other angle is the angle with the Z axis, which is pi. The Greek letter between Z and pho. 85 pho. That's a thing. I forget just where that lies in the Greek alphabet. Alpha's here, and omega's here. Phi Phi Pho Pho's about here, I think. Okay. Oh. It is not pronounced phi, it's pronounced pi in my presence. Some people pronounce it phi, which offends me terribly. Makes them seem subhuman. Even though the person locally who says it most often is way smarter than I am. A way better mathematician. And a good guy too. So his pronunciation isn't quite enough to make him an enemy, but it's almost. Not really the great guy. Okay, so this point is X, Y, Z, or R theta Z, or rho theta pi. Okay. So what's the volume increment? Well, if we've got an angular change of delta theta here. And okay, got an angular change delta theta here. We're talking about the delta theta by delta pi by delta rho increment up here. Okay. So we're going to have a delta pi. Not being drawn very well. And we have a difference delta rho, which is right along the line from the origin out to this point. So we get an increment up here. Going to be kind of like this. As we change pi, that changes the angle from the Z axis. So it's going to kind of come down this way. We're going to have actually kind of read that in the wrong direction. And phi is coming out this way. Let me pause and fix that picture a little bit. Okay, it's not a great picture, but I decided I didn't need to redraw it. I just took my delta rho and put it up here so it's clear. The delta rho goes out in the direction of the vector from the origin out to the point. Okay. So you got three sides of this thing. If delta rho, delta phi, and delta theta are all small, it's going to be close to a rectangle. Now you have this side here, which is because of the change in the angle phi. Okay, angle phi goes from up here down to here. So this side here is rho delta phi, and I'm not going to be looking for a place to label it, but we're going to finish something else. So that's going to be this side here. And this one, and this one, and this one. That's your second dimension. And your third dimension is the projection of this thing down here. Is just your blue before. Just your, I'll call it your blue instrument down here. Which is this distance here is r delta theta, this side. And what's r? In terms of rho and phi, r is rho sine phi. You can see the triangle. Maybe you can't see it. Let me see it here. Here's rho. Here's your projection down into the XY plane. And here's the angle phi. If this angle is phi, then this projection line is parallel to the z-axis, and this angle is phi. So that this side being opposite phi is rho sine phi. That makes sense. Can you see that? I need to draw it bigger and wave my hands more. Let me just say what I need to say again. This segment goes from the origin out to whatever your point is. Its length is rho. The angle between the z-axis and this line is phi. This line that projects the point down to the xy plane is parallel to the z-axis. So the line with length rho, the line from the origin out to your point, makes the same angle with the projection line as it does with the parallel z-axis. It's just okay. This angle is the same as this angle. And there's your YZ plane. If this is phi, this is phi, and this side here is opposite phi. This side is rho. So you got rho sine phi down here. The book will explain that to you. And you can always, you don't understand everything. It sometimes helps us to Google explanation of spherical coordinates or rectangular cylindrical spherical coordinates. You probably find a really good explanation there. It's better pictures than I've got. Okay, well, that's not bad. I'll tell you. Okay. Well, if this is r delta theta, which is rho sine phi, so is this. This is basically just a copy of this lifted up here. So that That's going to be this dimension. So your volume increment comes out this. You've got a row from this, and you got a row from this, and you're gonna have a row squared. You got a sine phi from this, then you just have a delta row up here. Put those together, there's your volume increment for spherical coordinates. Okay. The conversions are simple. Conversions between spherical and cylindrical are simple. Between spherical and rectangular, they're a little more complicated, but you just go through the cylindrical and it becomes easy. I'll show you what I mean. So first of all, in terms of R and Z and theta, what's rho? Well, rho is this hypotenuse of a triangle with a right triangle with legs of R and Z. So it's pretty clear that rho is R squared plus Z squared, right? And of course, R is just the square root of X squared plus Y squared. So you can get rho easily enough from X, Y, and Z. That's pretty simple. We saw that in the very first example. Reason that out from the origin of the point X, Y, Z, the distance is X squared, square root of X squared plus Y squared plus Z squared. And I didn't put my square roots in there. Okay. So now it's right. Okay. Then let's see. What's theta? Same in cylindrical and spherical. And our tangent of y over x plus pi if x is less than 0. Okay. That thing that we talked about here. And phi. Well, what's pi? What's pi related to? We got this triangle here. The phi, if we want to express that triangle in terms of r, theta, and z, what is it? What's the tangent of this angle? It's the opposite side over the adjacent side, right? The opposite side here is the same as r in cylindrical coordinates, just a projection from this point back to the z-axis at the right angle, and r projects in exactly the same way. So that this side is r and this side is z. It looks like just the arc tangent. Okay. Arc tangent of the opposite over the adjacent, arc tangent of r over z. And we don't need not r over z. Tangent of phi is opposite over Jason, which is all over C. Okay. The problem with that is, I don't have a problem with that. Okay. If Z is negative, it just gives you an angle. Actually, it's between, I mean, the angle is between 0 and pi. Okay. So I'm ready to say deal with that. It's that arc tangent. But the arc tangent is officially between negative pi and pi. And it's not looking right to me right now. I'm not going to worry about it. Pretty much it. Okay. You got our tangent with it. All right. And then if you know X, Y, and Z, it's not difficult if you see the triangles to I'm sorry, if you know rho, theta, and phi, you can find X, Y, and Z because rho sine phi gives the R, which is then multiplied by the cosine of theta to get X and Y, and sine of theta to get X and Y. So those are all pretty simple relationships. Now you got to be asked to do things like here's an equation in polar coordinates, write it in cylindrical coordinates. Or here's an equation of rectangular coordinates, write it in cylindrical coordinates or whatever, okay? And then you look at maybe some shapes. So I don't think you're gonna have too much trouble with it, but some things you're gonna have to think about if you didn't get them earlier. Okay.